In this section, we will present the basics of digital communications. Topics discussed in the basics of digital communications go a long way in order to understand the fundamentals involved in OFDM and single carrier communication systems. In particular, we'll talk about pulse shaping and modulation for communication over band-limited channels that also have power limitations, expressed in terms of limitations with the signal-noise ratio. With this introduction, we begin our development of the basics of digital communications, starting with baseband communications. So here we are interested in communicating over a band-limited channel with additive white Gaussian noise. In this case, we're dealing with a baseband channel with a bandwidth of W hertz. We're showing the two-sided spectrum of the channel frequency response. So the bandwidth is W hertz, and we have a mirror image over here dealing with a real system. So the idea is to transmit digital data, encode it, modulate it, such that we can transmit it through this band-limited channel with the provision that the bandwidth cannot exceed W hertz. This block diagram shows the baseband digital communication system, the transmitter. In this case, data is being generated, ones and zeros. For example, random. The data could go through a scrambler and be scrambled in order to randomize it. It's always a good thing to randomize the data, as we'll show later, in particular in terms of timing recovery performance. For the meantime, we're generating ones and zeros. We pass this through a coder, which maps the ones to a +1 and the zeros to a -1, for example. And we represent these coded symbols as impulses in time. The distances between the impulses is t, and the symbol rate is 1 over t, and we denote that by r sub s. The impulses go through a pulse shaper, which is a key block within the digital transmitter. The pulse shaper is such that the Fourier transform of its impulse response is a band-limited signal, such that the signal is band-limited within W hertz, which is a key requirement of our communication system, that the system has to be band-limited within W hertz. So since the pulse shaper is a linear system and we have a chain of impulses, each representing a symbol, which have been mapped from the binary ones and zeros, the output of the pulse shaper is a superposition of the impulse responses of the incoming signal. And each impulse response, by the definition of the pulse shaper, will be band limited to less than W hertz, and therefore we meet our requirements in terms of the digital communication length, the baseband digital communication length. Let's examine a pulse shape that meets our requirement that it is band limited in the frequency domain, and let's see what the trade-offs are. Here we show the channel frequency response. That is where we have to limit the baseband digital communication system so that it's transmitted within a bounded bandwidth W, not to exceed W hertz. If we take the inverse Fourier transform of a rectangular shape in the frequency domain, then we get in the time domain a sinc function. This is the well-known sinc function in the time domain. And it turns out that this sinc function will have a zero crossing at a point t, capital T, and periodic zero crossings distance t seconds apart. Also, another property of the sinc function is that since we are limited in the frequency domain, we have a hard limit, this is a rectangle, then due to the nature of the Fourier transform, the inverse Fourier transform, the signal in the time domain will be unbounded, unlimited. So we see that by restricting the bandwidth in the frequency domain, in the time domain, the inverse Fourier transform, the signal in the time domain it is not time limited. Of course, this is a well-known property of the Fourier transform and inverse Fourier transform. So one problem of band limiting a signal to a fixed bandwidth is that in the time domain we'll have a very long time extent, as is shown in the case of the sinc function here. If we have a filter which has an impulse response, which is the sinc function, then we know that in the frequency domain it would be band limited and will meet our requirements for transmission over a band limited channel. So in the case of the pulse shaper, if the pulse shaper has an impulse response, which is in fact the sinc function as shown, then the output would be band limited, and we will meet our requirement to transmit over a band limited channel. A couple of definitions are important. One is the symbol rate. So in this case, the zero crossing of the sinc function is at t. The symbol rate would be r sub s 1 over it. Also notice that the zero crossing in the time domain is related inversely to the bandwidth. That is t equals 1 over 2w. And you can see this from the inverse Fourier transform. If you're familiar with a pulse that has a pulse width of tau, then in the frequency domain you have a sinc function which the first zero crossing in the frequency is 1 over tau. So in this case we have in the frequency domain a width of 2w, and in the time domain we'll have the first zero crossing at 1 over 2w. So t is the symbol interval, and we'll show that next. Here we show the impulses which are input into the pulse shaping filter. The output of the pulse shaping filter would be the impulse responses, and using superposition the signal would be the addition of these impulse responses. So the actual signal would be the addition of these impulse responses. We'll show you a waveform later on. The timing between the impulse responses is t seconds. So we have t seconds between the impulses. And notice that because of the property of the sinc function, that the impulse following the first impulse, if it's followed exactly at t seconds, then at the peak of the second impulse response corresponds to the case where the first impulse response goes through 0. So we have 0 intersymbol interference at this point. Notice that for the third impulse also, that is spaced t seconds apart, also note that at its peak, both the first impulse and the second impulse both go to 0, so there is 0 intersymbol interference at this point in time. This is a very nice property of the sinc function and a whole class of pulses that we will discuss called raised cosine pulses, or Nyquist raised cosine pulses. So the symbol rate is 1 over t, and the symbols are spaced at t seconds apart, and t is related to the bandwidth. In this case, t is equal to 1 over twice the baseband bandwidth, and the symbol rate, of course, is 1 over t. So we've accomplished a number of things. One is we have a pulse shaper that generates impulse responses for each input symbol that are band limited and meet the requirements of the band limited channel. And we get a bonus in the sense that the resultant signal from pulse shaping using the sinc function have 0 intersymbol interference at the peak. So if we sample the signal at its peak, we will have 0 intersymbol interference, for example as shown over here. Now obviously if there's jitter in the sampling process, there's jitter in the clock, there's errors in the timing recovery, then we will get a large amount of intersymbol interference, and it is only 0 when we sample at the optimum time at the peak, as shown over here. Now, as we mentioned before, the problem with the sinc function is that although we meet the requirement that the signal is band limited, it is unlimited in the time domain. Its extent goes out from minus infinity to infinity, actually, and the side lobes die out very slowly. So another class of filters that we can use for pulse shaping are called raised cosine Nyquist pulse shaping, and they have a very nice property in the sense that for all the filters that we show over here, in the time domain they have 0 crossings at the symbol time and satisfy our 0 intersymbol interference requirement. And we'll discuss that in a minute. For now, let's focus on this class of filters. We show actually 3 filters over here. One is the filter with a rectangular frequency response, and we know that its impulse response is the sinc function that we described. But as we mentioned, if you limit the signal and energy in the frequency domain, then it spreads out in the time domain. So by broadening the spectrum in the frequency domain, we actually shrink the time domain, and therefore we may get some better results in terms of both implementation and intersymbol interference. The filter shows 3 domains. In one domain, the filter is always 0, which is when the filter is less than W, the bandwidth. So W designates the bandwidth. For a band-limited system, we want the frequency to be 0 when it exceeds W. In between, we have a class of filters that can be changed by specifying different values for W and W sub 0. W0 is a frequency in which all of these filters that you show over here exhibit a symmetry about this point. And this is a key requirement, as we will discuss. Having symmetry about this point as shown ensures that in the time domain, all the impulse responses of these filters, these pulse shaping filters, would have 0 crossings at fixed periods. We'll show that in a minute. This filter here, called the raised cosine filter, is for the case where the bandwidth is twice W0, and we can get filters in between. Let's focus on this diagram here. We can associate with each filter a parameter beta, which is called the roll-off factor. For beta equals 0, we get the rectangular frequency response, and for beta equals 1, we get the system with a maximum bandwidth shown over here. For beta equals 0.5, we get filters in between, and notice that these filters all are equal to 1 up to a certain point, and then they have the relationship with the square of the cosine as shown over here. So they all have a case where they're equal to 1, then they fall into this region here, and then of course there's 0 beyond the bandwidth W. So in this figure we show 3 filters. Let's take this particular filter here. For any particular filter, we have that the bandwidth is equal to W. For this particular filter, the bandwidth is, here's plus W and here's minus W. So this filter has a bandwidth of W hertz. Now, it turns out that the bandwidth is related to the symbol rate, R sub S. Recall that the symbol rate is the inverse of the spacing between the symbols. And they're related by the roll-off factor beta. So let's take a look at this. For beta equals to 0, we get that W, the bandwidth, is half the symbol rate. This is the case over here, where W, the bandwidth, is actually equal to half the symbol rate. For the case that beta is equal to 1, we get that the bandwidth is equal to the symbol rate, which is this case here. And for any value in between, we get a class of filters that all belong to the class of raised cosine Nyquist filters. If we rearrange terms, we can write the symbol rate in terms of the bandwidth and the roll-off factor. And this is a very interesting equation because in a communication system, the bandwidth will be specified. W is fixed. For example, it's 100 kilohertz. This shows that for beta equals to 1, for example, the symbol rate is equal to the bandwidth. However, for the case where beta is equal to 0, the symbol rate is twice the bandwidth. This is very interesting. This shows that by controlling the roll-off factor, by thereby controlling the amount of excess bandwidth, as you can see over here, we can actually improve the throughput through the channel. So the maximum throughput through the channel is achieved with beta equals to 0. And if we use beta equals to 1, then we get half the throughput of the maximum throughput. So there's a basic trade-off between having a filter which is broader in the frequency domain and therefore time limited, which is what we need, and at the same time the throughput of the system. Beta is called the roll-off factor. Also, it controls the excess bandwidth. So for example, for beta equals to 1, we have 100% excess bandwidth. In the case of beta equals to half, we have 50% excess bandwidth. And the case where we have a rectangular pulse, of course, we have 0 excess bandwidth. In this diagram, we're illustrating the relationship between the symbol rate, and the bandwidth and the roll-off factor. So consider the case here where we have a bandwidth of W hertz, so we have a channel that is band limited to W hertz, and we have the various raised cosine filters with roll-off factors, beta equals 0 for the rectangle, beta equals 1 for the case where we have 100% excess bandwidth, and beta equals to a half for 50% excess bandwidth. For each one of these cases, if we refer to this relationship here, we see that for beta equals 0, that the symbol rate is twice the bandwidth, so we get the highest throughput with beta equals to 0. For beta equals to 1, we get that the symbol rate is equal to the bandwidth. So we have at the maximum throughput, we have that the symbol rate is twice the bandwidth, and in the case where we have 100% excess bandwidth, then the throughput is equal to the bandwidth. And we get different symbol rates for different values of the roll-off factor in between. This basically shows that we can achieve higher throughput using different values of beta, and this comes at a cost, as we will show when we look at the impulse response for the various raised cosine filters. And this to be expected that for lower values of beta, even though we get higher throughput, but in the time domain we have to worry about clock jitter, and the fact that if we have clock jitter we can introduce intersymbol interference if beta is small. So there's a trade-off between the complexity of your clock recovery and timing recovery and the higher throughput. However, in many communication systems, the system is designed in order to support lower roll-off factors in order to enhance the throughput through the system. In fact, let's take a look at the parameters used in 802.16a. So over here we're actually showing the baseband pulse shaping from 802.16a for a single carrier metropolitan wide area network. In this case we're using a single carrier communication system that can use, for example, a modulation of QPSK or 64 QAM. And for the I and Q signals, they actually use a square root raised cosine filter in order to do pulse shaping, and a roll-off factor equal to 0.25 is used. And as an option, you can use roll-off factors equal to 0.15 and 0.18. So these, of course, result in higher throughputs. So what we're talking about is actually very relevant in digital communications and is used quite often in single carrier systems, and especially in terrestrial microwave links. We'll come back to these equations a little later. Let's go ahead and take a look at the impulse responses of this family of pulse shaping filters in the time domain. This is a very important formula, which is the formula for the impulse response for the class of filters that were the raised cosine Nyquist filter. For all cases of beta, notice that we have 0 crossings at time intervals t seconds apart. So when t is a multiple of capital T, then we get 0 for the impulse response. So that's shown over here for the case of the sinc function, which is beta equals to 0. We have the sinc function, and we have 0 crossings at t seconds apart. But that also holds true for all other impulse responses for beta equals to, for example, 1 and beta equals 0.5. So all these pulse shaping filters have a nice property of having 0 crossings at equal intervals of t seconds apart, such that they have 0 intersymbol interference. The symbol rate is 1 over t. So let's go back to this diagram here. For the case that beta is equal to 1, we have a broadening in the frequency domain that results in a limiting in the time domain. So you see that the impulse response for beta equals 1 dies off very quickly, and we have a crunching up or limitation in the time domain because we broadened it in the frequency domain. In the case of beta equals 0, We limit it in the frequency domain, and then we, of course, broaden out in the time domain. And in between, we have a trade-off for different values of beta less than 1. One very important point about these raised cosine filters is to take a look at the impulse response in the time domain. As beta increases, we see that in the denominator increases with beta and also the power of t, so that the side lobes die out much quicker over time, the higher the value of beta. And that fits well with a case where for beta equals to 1, where we brought in the frequency domain, the time domain becomes more and more limited. This is also very important in terms of intersymbol interference. The case with the most possibility for intersymbol interference when you have timing errors is the case where beta equals 0, where you have the sinc function. So there's a trade-off between intersymbol interference and throughput and usage of the bandwidth. Going back here, we see that if we have a fixed bandwidth W, then for beta excess bandwidth less than 100%, we can actually achieve a higher throughput through that channel compared to the case where we have 100% excess bandwidth. The cost of that is, of course, more intersymbol interference. So for the case where beta equals a half, or we have 50% excess bandwidth, then compared to the case where beta equals to 1, we have more significant intersymbol interference, potential for intersymbol interference, but we get a higher throughput. In the extreme case where beta equals to 0, the throughput is actually twice the bandwidth. The symbol rate is twice the bandwidth. Let's take another look at the situation we have. We have the coder generating impulses, which are spaced out at t seconds apart, and they are input to a pulse shaper. And the output of pulse shaper is the impulse response for each impulse. And we have that the signal is a superposition of these impulse responses. And here we're showing the case where you have 0 excess bandwidth, the case where you have a sinc function. In the time domain, we will have a superposition of all the impulse responses. And we get a signal as shown over here. For this particular case, beta equals 1, and we have 100% excess bandwidth. Now, in digital communications, we need to look at this signal from a different perspective. If we take a fixed interval, for example, over 2 symbols, and we fix that interval and overlap all the time domain signals over that interval, we get what you call an eye diagram. So here is the eye diagram for beta equals to 1, or 100% excess bandwidth. We see that the eye diagram gives us a much more informative view than just the time domain signal shown over here. So by generating the eye diagram, by overlapping the signals over a fixed symbol period, we get the curve shown over here. And because of the 0 intersymbol interference characteristic, or 0, or the periodic 0 crossings that is characteristics of the Nyquist pulse shaping filters, we get this eye diagram where over here we see that we have 0 intersymbol interference and the eye is open. This is for 100% excess bandwidth. For the case of 50% excess bandwidth, or beta equals to a half, we still see that we have an open eye. However, because of the fact that in the time domain the signal has greater side lobes than in the case of 100% excess bandwidth, we have more of a chance of intersymbol interference in the case where we have clock jitter. So let's take a look at this. For the case of beta equals a half, we see that compared to the case of beta equals 1, we have greater side lobes in the time domain. So comparing the two, we show the eye diagram for the case where beta is equal to 1, or 100% excess bandwidth, to the case where beta equals a half, or we have 50% excess bandwidth. If we have jitters in the clock and timing errors, in the case of 50% excess bandwidth, we see that if we make errors in this part here, we see that we get a large amount of intersymbol interference, whereas we can tolerate quite a bit of clock jitter error around here where we get much less intersymbol interference. This is the trade-off that we have in using a value of beta less than 1. However, notice that for the case where beta is less than 1, we achieve a higher symbol rate over a fixed bandwidth channel. So there's a trade-off to increase the symbol rate at the expense of intersymbol interference due to clock jitter, timing errors, or by reducing the throughput and being more immune to clock jitter errors. So that is a basic trade-off. Many times systems will be designed with where beta is equal to 0.5, or we have 50% excess bandwidth, or even less, and the system is designed such that it tolerates the timing jitter and we still achieve the performance we require, but at the same time we achieve higher throughput. Here are the results of the actual simulation of a baseband digital communication system with Nyquist pulse shaping. Here we show the case where we have 100% excess bandwidth, and we have random ones and zeros that are mapped to impulses plus and minus 1 that are then input to the pulse shaping filter and transmitted through the channel. In the case of beta equals to 1, the required bandwidth is 1.25 megahertz, as shown over here, where we have the frequency in megahertz. So at this point we got 1 megahertz, and over here we have 1.25. That's the bandwidth required for the case where we use 100% excess bandwidth. If we use a roll-off factor beta equals to a half, then you can see that our bandwidth requirements have shrunk, and the total occupied bandwidth is at 0.9375 megahertz. And this is going back to this equation over here, where the bandwidth is related to the roll-off factor to the symbol rate. In this case, the symbol rate was 1.25 megasymbols per second. Here we will examine the baseband digital communication link. We have data that generates random ones and zeros with a 50% chance of a 1 and 50% chance of a 0 equally likely. We have a coder which maps a 1 to a plus 1 and a 0 to a minus 1. These are our symbols. And we have an upsampler which inserts zeros generating impulses. So we have an impulse for the first symbol and we have an impulse for the second symbol, for example. These impulses are input to a square root Nyquist pulse shaper and then transmitted through a band-limited channel with a bandwidth of W hertz. We have additive white Gaussian noise, and at the receiver we have a square root Nyquist pulse shaper, which is the match filter to the transmit filter, which is also a square root Nyquist pulse shaper. Assuming perfect timing, we sample at the maximum signal-to-noise ratio, and we'll explain that subsequently, and downsample by a factor of 8 in this case, and we obtain the decision variables ace of 0 if a minus 1 was sent, corresponding to a 0, or a decision variable a1 corresponding to the case if a 1 was sent, corresponding to a binary 1. And a decision is made through the slicer. We'll explain the threshold here, which is at 0. If the signal was above 0, we make the decision that a 1 was sent. If the signal is below the threshold of 0, we assume that a 0 was sent. The combination of the square root Nyquist pulse shape filter at the transmit and receiver is a Nyquist pulse shaping, so we get at the receiver, in the case of no distortion in the channel, which we don't have, a eye diagram that is shown over here. In the figure over here, we are using a 100% excess bandwidth or roll-off factor equal to 1. If we go back here, we see that the impulses are input to the square root Nyquist pulse shaping filter, and here we show that the output of the square root Nyquist pulse shaper is a superposition of impulse responses. Each impulse response is the symbol for a Nyquist raised cosine pulse, which, as we have indicated before, has 0 crossings at equal intervals. So at the sampling points shown here, we have 0 intersymbol interference from the pulses. That is a nice property of the raised cosine filters. The spectrum at this point is band limited. We're actually showing the results of a simulation here, and we see the characteristics of a raised cosine filter, and it is band limited to 1.25 megahertz. The bit rate is 1.25 megabits per second, and since we're using 100% excess bandwidth of a roll-off factor of equal to 1, the bandwidth is also 1.25 megahertz. The bandwidth of the channel W is also equal to 1.25 megahertz. In the next section, we will explain the operation of a match filter at the receiver, which is the optimum receiver for the case where we have additive white Gaussian noise, and a maximum likelihood detection scenario, in which case we're assuming that the data symbols 1 and -1 are equally likely. And we'll come back to this block diagram as we discuss the different components of the block diagram in more detail. Here we show the simple model of the case where we have the square root Nyquist filter at the transmitter, which could be a raised cosine Nyquist filter. And at the receiver, we have the square root Nyquist filter, which is a matched filter to the transmit filter. If the impulse response of the transmit filter is h of t equals to p of t, then the impulse response of the match filter is h of t equals to p of capital T minus t. And just for illustration purposes, here we show a pulse shape for p of t. So if p of t has this pulse shape shown over here, duration t, where t is a symbol time, then the match filter p of capital T minus t, first of all, because of the minus t, will have the mirror image shown over here. So we would have the mirror image here, but delayed by t, so it's shifted by t, as shown over here. So this is the impulse response of the match filter to the transmit filter. Without going through too much detail, just to point out that when the impulse response of a filter is the match filter as shown, especially since we have a mirroring in the time, we have negative time here, then when this signal is input to this filter, we will get a cross correlation between the transmitted pulse and a copy of itself at the receiver. So we will have a case where we have maximum correlation when the pulses overlap, and that will correspond to the maximum opening of the eye, and that's exactly where we would sample under perfect timing recovery, and at that point we would have maximum signal to noise ratio. Now, since this is the pulse that is input to the match filter, and the match filter has the impulse response shown, the output of the match filter would be the convolution in the time domain between these two signals, the actual input pulse and the impulse response. Here's the expression for convolution, and we won't go through too much detail, but as you may recall, in convolution we have the signal y of lambda, and here in this case we have p of lambda as a function of lambda, and x of t minus lambda, and notice that we have x of minus lambda, so we have a mirror image of the impulse response. So if this is the impulse response here, we need to get its mirror image because we have minus lambda. So notice that the match filter, which was already the mirror image in the convolution, then it gets flipped again and actually becomes the pulse itself. And as time varies, we shift the pulse, and of course we multiply the two and integrate for every time and obtain the convolution as a function of time shown over here. So as we perform the convolution and this signal moves across, x of t minus lambda moves across, then at one point we would have complete overlap of the two signals. At that point we have the maximum signal to noise ratio, that's the optimum sampling point, in order to come up with the decision variables. And in the eye diagram, that's the point right over here in the case that a +1 was sent, and here in the case of where a -1 symbol was sent. So think of the match filter as performing a cross correlation between the transmitted pulse and a local copy of the pulse, where we get a complete overlap. We have maximum signal to noise ratio, and that's the optimum point to sample, and that value is then used to make decisions on which symbol was sent. There are many ways to look at match filtering in terms of a correlation operation or a filtering operation. Let's take a look at the operation of a match filter. The input to the match filter at the receiver is a transmitted pulse at an amplitude A, and if we increase the power of the transmitter, then A increases. So A would be related to the signal power, the transmitted power. P of t is a pulse shape of the transmitted symbol, which going back here, as we indicated, we have impulses going into the Nyquist pulse shaper, the square root Nyquist pulse shaper, and the output would be a impulse response corresponding to a symbol, and that impulse response, piece of t, would actually be the raised cosine type pulses that we have shown before. For example, for the case of beta equals to 1 with 100% roll-off factor, it would be this pulse over here, we can show. Again, notice that in the time domain, the raised cosine Nyquist pulse shapes all have zero crossings at the symbol interval. So PT corresponds to a pulse of the square root Nyquist pulse shaping filter as we showed. And that is what is transmitted. It is input at the receiver to the match filter. Of course, we have additive noise, but in this case, we want to just analyze the response of the match filter to the signal itself. We will discuss the response of the match filter to the noise separately. So if the input signal is APT and the match filter has an impulse response which is P of capital T minus T. So going back to this figure here, at the maximum signal to noise ratio, these two pulses actually overlap, and we multiply them. If we look at here, we multiply them, and since they're exact copies, then we get the signals squared, integrated over lambda from minus infinity to infinity. So the actual value at time t, the sampling time t, the maximum eye opening, or the point of maximum signal to noise ratio, the value would be equal to A times the integral of the pulse piece of tau squared d tau. Now this turns out to be the energy, by definition, the energy of the pulse. In our case, the square root Nyquist raised cosine pulse. Now the Fourier transform of P of t is piece of f. So piece of f is the frequency domain representation of the signal piece of t. And because of Parsifal's theorem, the energy in the time domain is equal to the energy computed in the frequency domain, which is the area underneath the magnitude squared of the frequency response, as shown over here. And think of the magnitude piece of f squared as the energy density, and as we integrate it over all frequency, we get the total energy, which is equal to the energy computed in the time domain. So these two numbers are equal, and this is going to be very important because later on we are going to use the representation here for the value of the signal, the decision variable at the output of the match filter, as we sample at the optimum t where the eye is maximally open. And we have the maximum signal to noise ratio over here. So we are going to get two decision variables, A0 or A1, depending on whether a 1 or a minus 1 was sent, corresponding to symbols 1 and minus 1. And the number in the case that a minus 1 would be sent would be minus A. In the case a plus 1 would be sent would be plus A. And we will use either representation for the value of the decision variable as A1 or A0. Now here we show the operation above in more detail. Here we have the square root Nyquist pulse-shaped filter in the time domain, so we have the single piece of t, and we have piece of f, its Fourier transform in the frequency domain, and we note that it is band limited to b hertz as required. We receive the single a p of t, and if we wanted to compute the energy of the single a p of t, then we can either compute it in a time domain, where we take the signal, square it, and integrate it, which we're doing over here, over all time, times the amplitude squared, that would be the energy of this pulse. And since this pulse represents 1 bit, which in our case 1 bit is equivalent to 1 symbol, we have a 1-to-1 mapping because we are a binary system between a bit and a symbol, then this is the energy per bit. Now, if we go back in the frequency domain, piece of f, the magnitude piece of f squared is the energy density as a function of frequency. And if we integrate in the frequency domain over the energy density, then we get the energy in the frequency domain, and we have an amplitude a squared, a, so the amplitude becomes squared, so the energy in the frequency domain is equal to this expression, and both of them are equal due to Parsifal's theorem. So either way, these two expressions can be used to compute the energy per bit. Going back to our baseband transmission system, we have additive white Gaussian noise that is also input to the received match filter along with the signal. And due to the linearity of the system, the output of the filter is the sum of the contribution of the noise going through the filter and the actual signal going through the filter. So here we want to analyze the noise. Here we analyze the noise. In the plot shown over here, we are plotting around 2,000 samples of a Gaussian noise process with a RMS equal to 1. The mean value is equal to 0. Now the probability density function for a Gaussian noise process is shown over here. We have the normal distribution, and we know that the integral of the probability density function from x equal to minus infinity to plus infinity is equal to 1. That is the probability that the event will occur is equal to 1. A Gaussian random variable can have a mean value m of x. In our case, it's equal to 0. And it has a standard deviation, sigma of x, shown here. The normal distribution is shown by this expression over here. So we have p sub x is equal to the following expression. Notice that we have included the mean value, and sigma x squared is the variance. This is the famous equation for a normal distribution. Now here we want to analyze the output of the match filter with an input which is a white Gaussian noise process. Going back to the baseband digital communication link, we have the noise, which is additive white Gaussian noise, going through the match filter, the square root Nyquist pulse shaper, and we are interested in the output of the match filter due to the noise input. Additive white Gaussian noise, in our case, is white noise, and it has a one-sided power spectral density equal to N0, and here we're showing the two-sided power spectral density, and therefore it is equal to N0 over 2. Now theoretically the bandwidth goes out to infinity, but in practice it doesn't. There is always filtering going on, but we can assume that over the bandwidth of interest that it is white, it's flat. The noise is input to the match filter. The match filter has a frequency response which is equal to P conjugate of F. Recall that the impulse response of a match filter was P sub capital T minus T, so the minus T creates the mirror image. In the frequency domain, that corresponds to conjugation. But in general, if we have a filter with a filter response P sub F, as shown over here, band limited to B hertz, and we pass additive white Gaussian noise through that filter, the output of the filter would also be Gaussian noise. It is no longer white because it is band limited. In fact, it is correlated, but it is still a Gaussian random process. Now, what is of interest to us here is what is the variance of the noise at the output of the match filter. Now, for any filter shown here, if we take any generic filter here that we pass additive white Gaussian noise through that filter, the variance of that noise, which is equal to its power, would be equal to the integration over the whole power spectral density. So we integrate from minus infinity to infinity of p sub f squared. Now since n0 is a constant, it will come out of the integral. So we integrate basically the area underneath p sub f squared, and in that case it doesn't matter whether you have p sub f or p conjugate of f, and we obtain the variance of the noise at the output of the match filter. So to summarize, we have an expression for the variance of the noise at the output of the match filter. It is Gaussian noise. However, unlike the input, which was white Gaussian noise, in this case we have correlated band-limited Gaussian noise. It is important to be able to calculate the variance of the noise in order to compute the signal-to-noise ratio, because this is the noise that would be in the denominator in the computation of the signal-to-noise ratio at the decision point. Going back to our block diagram, we sample at the maximum eye opening, and when we have additive Gaussian noise, at the maximum opening we will have a signal-to-noise ratio between the signal power and the noise power at this sampling instance. And in fact, a match filter is the filter that maximizes the signal-to-noise ratio at the optimum sampling point by definition. So now we have a means for calculating the power of the signal and the power of the noise, so we can compute the signal-to-noise ratio. Now, as this block diagram shows, we obtain at the receiver two decision variables, a sub 0 and a sub 1. We obtain the decision variable a sub 0 in the case a -1 symbol corresponding to a 0 was sent, and a sub 1 if we transmit a symbol equal to 1 corresponding to a binary 1. Now this is a very important diagram. Here we show the actual symbols that are sent in a constellation diagram, but basically this is the symbol corresponding to A0, and this is the symbol corresponding to A1. At the receiver, we receive these signals with additive noise effects, so that the signals that we actually receive will not be at the ideal point, but would be scattered about. And sometimes, even though we sent a 0 corresponding to a -1 symbol, the noise could be such that it gets closer to the side where the actual signal corresponding to a +1 was sent, and we can easily make the error of decoding that as a +1 even though a -1 was sent. That would cause an error in the digital communication link. Again, if we look at the diagram over here, we're inputting a signal a p sub t. In this case, a being positive, it corresponds to A1. It goes through the match filter. We also have noise, and we sample at the point of optimum sampling point, which is the maximum signal-noise ratio, and we obtain the decision variable A1. Here we show the probability density function, PDF, of the decision variable A1. The mean value would be A1, shown over here, corresponding to this point here. However, because of the noise, we will have a normal distribution around that, corresponding to the noise in the channel. The variance of the noise is computed as shown over here, so it's equal to sigma n squared, is the variance of the filtered noise, as the noise is filtered by the match filter, as shown over here. Now in the case where we send the symbol -1, then we have minus apt, and we get the decision variable a sub 0, and again we have a normal distribution because we have additive noise added to it, Gaussian noise, and we get the PDF shown over here, and the variance of the noise is equal in either case. So here we have the PDF in the case that a -1 symbol corresponding to 0 was sent. Here we have the PDF for the case where a +1 corresponding to a binary 1 was sent. So this curve here represents the probability of the received signal Z given that S0 is sent, or -1, and the PDF here, the probability density function of that is equal to p sub Z given that S1 is sent, corresponding to the symbol 1. Now in a maximum likelihood receiver, we assume that the symbols S0 and S1 are equally likely. And from this diagram here, because of the symmetry between A0 and A1, now because of the fact that A0 is equal to minus A1, the threshold for making a decision is 0, and that makes a lot of sense in here, in this figure here. So if the signal appears in this location here, we make the decision that S1 was sent. If this received decision variable is in this region here, we assume that S0 was sent. If S0 was sent, but the received signal occurs in this location, then we make the decision that S1 was sent, then we have an error. The question is, what is the probability that we make this error? We can see that in the following diagram. Now here we have the probability density function of the variable Z, the sampled output of the match filter at the optimum sampling point, maximum signal noise ratio. And this area shown over here is the probability that we sent S0, but we make the decision that S1 was sent. The probability is equal to the area underneath the tail of the normal distribution as shown over here. So the area underneath here is the probability that we have sent S0, but we decode it as S1. Likewise, the shaded area here is the probability of an error given that we have transmitted S1, but since we exceed, we become negative, we decode it as S0, and therefore we make an error. The probability that that happens is the area underneath the tail shown over here. So the area underneath this tail is denoted by the probability of error given that S0 was sent, and the area underneath the tail shown over here is the probability of error given that S1 was sent. So this makes a lot of sense. Our threshold is basically 0. If we send a signal S1 and we receive a negative value, then we make an error. So what is the probability that we get a negative value given that we sent S1? It's the area underneath this tail. And the same applies for S0. The total probability of error is the probability of error given that S0 was sent, which is equal to the probability of error given that S0 times the probability that S0 was sent in the first place, plus the probability of an error given S1 times the probability that S1 was sent. Now, as we mentioned, we were talking about a maximum likelihood decoder, and we indicated that the output of the data generator was random ones and zeros and both equally likely. So the probability of S0 is equal to the probability of S1, which is equal to a half. So the probability of a 1 or a 0 is equal to a half. Going back to the figure over here, we see that the probability of E given S1 is equal to the probability of E given S0. And if we substitute a half here, and both of these are equal, we finally obtain that the probability of error is equal to the probability of E given S0 or the probability of E given S1, either one. So let's take a look at that. If we take this particular case here, then we show that we can compute the probability of error as the area underneath the tail over here. So we have the PDF of p sub Z given S0, which has a mean value A0, and the probability that of this, the tail here, is we have to integrate it over the threshold point. out to infinity, which is the area underneath the tail here. So that's the expression over here. So we have the probability of z given as 0 is this expression here, which is a normal distribution. Notice that the variance is sigma n squared, and the mean value is a0. And we integrate from the threshold value, which is a0 plus a1 divided by 2, which in our case, because a0 equals minus a1 is equal to 0. So we integrate from 0 to infinity, and we plug in the normal distribution shown here, and we get the probability of error. So here we have the expression for the probability of error for the baseband digital communication link. And the performance of a digital communication link will be determined by the probability of error versus the signal to noise ratio, or as we will point out, the EB over N0 ratio, where EB is the energy per bit and N0 is the one-sided noise spectral density. However, we need to come up with a more compact expression for the probability of error, and to do that we introduce the Q function. We define the function q sub x, which is equal to 1 over 2 pi, the integral from x to infinity of e to the minus u squared over 2 du, integrated over u. As it turns out, this function is very useful for the expression for the probability of error, because if you make a change of variables in the expression for the probability of error, you can actually express the probability of error in terms of the Q function with argument equal to a1 minus a0 divided by 2 times sigmas of n. The Q function, q sub x, is tabulated. That is, if you want to actually evaluate q sub x, you have to refer to tables. However, for x greater than 3, there is a very good approximation for the Q function. So q sub x is then equal to 1 over x square root of 2 pi e to the minus x squared over 2. So for x larger than 3, we see that the function, first of all, is monotonically decreasing, and it decreases rapidly as x increases, because we have the exponential e to the minus x squared over 2. And we, of course, have x in the denominator here. So this function rapidly goes to 0 as x becomes larger, and that's as we expect. As a1 minus a0 becomes larger, let's refer to this diagram here. Here we have the case for a0, and here we have the case for a1. Recall that a1 was sent when we sent a1 was received when we sent s1 equal to plus 1, when we sent s0 equal to minus 1. a1 minus a0 is this distance over here, and we see here that as this distance becomes larger, then the probability of error becomes small and rapidly goes to 0, close to 0, as this distance increases. Now this distance here is related to the square root of the energy. So in effect, what we're saying is that as a signal to noise ratio increases, the probability of error decreases, which is what we expect. We get better performance as the signal to noise ratio increases. This is also nice about the Q function, and the fact that the probability of error is expressed as the Q function related with the distance d between the 2 points. In digital communication systems, we need to actually plot the probability of error versus the ratio E sub b, which is the energy per bit, divided by n sub 0, which is the one-sided noise spectral density. Therefore, we're going to go through some mathematics in order to express the probability of error in terms of EB over N0, and that's what we'll do next. So even though this slide is kind of crowded, we've actually covered a lot of it in the previous slides, and we'll go through it step by step. First of all, we have the expression for the noise variance, which we derived before. So if you have noise going through a match filter, then we get the filtered noise n sub t. Its variance is equal to the expression over here, where n0 is the one-sided noise spectral density, and p sub f, magnitude of p sub f squared, is the magnitude squared of the match filter frequency response. A0, recall, was equal to minus a, since we're sending a minus 1 symbol times the integral of piece of f squared df. Now recall that, as shown over here, when we send the signal a piece of t, or in the case where we send the minus 1 symbol, we have minus a piece of t, and we pass it through the match filter. The output of the match filter is sampled at the optimum time t at the opening of the eye, and the output of the filter was equal to a times the integral of piece of tau squared d tau. Recall that in the match filter, as the correlation, we had maximum correlation, or the area underneath the pulse squared. So that was the value where we have maximum signal to noise ratio at the sampling point. And because of Parseval's theorem, we can also express this in the frequency domain, and these two are equal. So at the point that we sample t, we have the maximum signal to noise ratio, and the value at that point is equal to a integral minus infinity to infinity magnitude piece of f squared df. So that's where we get the expression for a1, and we also get the expression for a0, and the negative sign for a0 since we're sending the minus 1 symbol. So what we need to do is then substitute for a0 and a1 in the expression for the probability of error over here, and also substitute for the RMS value of the noise. Now, it'll be convenient to actually square this term as shown over here and then substitute for a1 and a0. So if we do that, since we have 4 times sigma n sub squared, we can substitute for sigma n sub squared over here, and this is the expression over here for sigma n squared. Now a1 minus a0, if you look at this expression here, becomes 2a times this integral, and when we square it, we get 4a squared and the integral squared. Now here's the beauty, is that in the denominator we have the same integral, so we can actually cancel these two out, and we're left with the expression below where we have only one term here, and we have n sub 0 in the denominator, and the 2 goes on top and the 4's cancel out, and we get this expression over here. Now if we pay close attention to this expression, we need to focus on this term over here, where we have the expression a squared times the integral minus infinity to infinity of the magnitude piece of f squared df. Now recall the signal energy for the transmitted pulse with magnitude a, and this is the expression for E sub b, which is the energy per bit. So we summarize that over here. For the receiving signal APT, the energy is E sub b, the energy per bit, a squared times the integral minus infinity to infinity of piece of f squared magnitude squared d sub f. Then we can substitute here for EB, so we get that a1 minus a0 squared divided by 4 sigma n squared is equal to 2EB over n0, so that a1 minus a0 divided by 2 sigma squared is just a square root of 2EB over n0. So if we go back to the expression for the probability of error, then we can express the probability of error in terms of EB n0, the square root of 2 EB over n0. Now I know that you've been patient and we worked through the math, and you might have to go back to the back and forth between the diagrams in order to validate and check the results, but the final result is that the probability of error for a binary system in a digital communication link, in this case for a baseband binary digital communication link, we get that for additive white noise the probability of error is equal to the Q function with argument square root of 2EB over n0. And this is the key. We need to express the probability of error in terms of the energy per bit divided by the one-sided noise spectral density. Now EB over n0 is related to the signal to noise ratio, obviously, because EB is related to the energy of the bit and n0 is related to the additive white Gaussian noise in the channel. However, as we will discuss later on, it is very important to be able to express the probability of error in terms of EB n0, and that's what we've accomplished over here. And we'll come back to this later. Now, Here we show a plot of the probability of error, this expression right here, as a function of EB over N0, and as indicated for a matched filter reception of a bipolar baseband signaling, which is what we've been discussing. So we get the following curve where EB over N0 is expressed in dB, and as EB/N0 increases, that corresponds to increasing of the signal to noise ratio. And here we have the probability of error, and note that at EB/N0 equals to 10.5 dB, we get a probability of error of 10 to the minus 6. This is important because in OFDM, using binary phase shift keying, or BPSK, this is the actual probability of error that we're looking for. This is our target right over here in some of the OFDM systems that we'll be discussing. So to summarize, we've been able to actually design a baseband binary digital communication link, and we have derived the probability of error versus EB over N0, the energy per bit divided by the one-sided power spectral density. That is, we're also relating it to the signal to noise ratio. So this is a major accomplishment in terms of understanding of a baseband digital's communication link with additive white Gaussian noise. So far we have described a baseband digital communication link. Next we consider communication over bandpass channels. Here's an example. We are showing 4 channels in the upper uniband for 802.11a. Each channel has a bandwidth of 20 megahertz, and because of the guard interval, the actual useful bandwidth in which information is transmitted is 16.5 megahertz. Each carrier is spaced apart at 20 megahertz, so this is an example of a case where the data has to be transmitted over a microwave length at a certain carrier frequency, for example in this case 5.765 gigahertz. So in communication systems over bandpass channels, we have to take the baseband information and modulate it up to a carrier frequency and then transmit at that carrier frequency. Many examples of bandpass communication systems exist. For example, voiceband modems, in which the bandpass channel is from 300 Hz to 3.4 kilohertz, and data rates up to 33 kilobits per second, for example, are supported. In the case of OFDM, we will take a baseband signal and modulate it up to a carrier frequency for a particular channel, for example 5.785 gigahertz. So next we will describe quadrature modulation, and we will describe a QPSK digital communication link. Before we do that, we need to go over some background, in particular modulation. Here we show the modulation property of the Fourier transform. If we have a signal x of t in the time domain with a Fourier transform x of f, then x of t times e to the j2 pi f0 t is a signal which has a Fourier transform of x of f minus f0. That is, modulation in the time domain results in a frequency shift in the frequency domain. This is the basic property of the Fourier transform. We can express cosine 2 pi f0 t as a sum of e to the j2 pi f0 t plus e to the minus j2 pi f0 t. The sine term cancel out, we get 2 times the cosine, and if we divide by 2, we get the cosine of the angle. Therefore, if we multiply x of t times the signal cosine 2 pi f0 t, then in the frequency domain, we get that the Fourier transform of x of f gets shifted by the frequency f0. So this is the modulation using a real signal. Here's an illustration of the modulation. X of f is shown here in baseband, has a bandwidth of b hertz. We modulate it with an oscillator designated by cosine 2 pi f0 t, and we get the output signal, the modulated signal z of t. If we take the Fourier transform of z of t, based on the expression over here, we obtain the spectrum x of f shifted by plus f0 and minus f0, and of course with a scaling factor of 1/2. In the following, we would always use a two-sided spectrum unless otherwise noted, in which case we'll point out that we're showing a one-sided spectrum, for example in simulation results. So this is the basic modulation theorem that we're interested in. If we have an oscillator at a frequency f of 0, then we can modulate the baseband signal x of t to the frequency centered on f0, and then of course pass this through a bandpass channel, and we have achieved our aim of transmitting signals over a bandpass channel at a carrier frequency. Another aspect of digital communication length is that given a fixed bandwidth, how can we increase the throughput through the channel? Previously we showed binary communication system in the case where one bit was associated with a symbol. For example, a 1 was associated with a symbol +1, a 0 was associated with a symbol -1. We need another way in order to improve the throughput, especially if we have high signal-to-noise ratio available. One way to do that is to use the constellation shown over here. In a constellation, we basically have analog signals that can also be represented digitally, but think of them as analog in a two-dimensional space. We have the in-phase channel and the quadrature phase channel. We have the in-phase axis and we have the quadrature axis. You can also think of the in-phase axis as the real axis and the quadrature phase axis as the imaginary part. Within the two-dimensional space, we have points, in this case 4 points. Each point corresponds to a vector, and each vector represents a symbol. And each symbol has a coordinate, an in-phase term and a quadrature phase term. For example, the coordinate over here, the point over here, has coordinates I equals to -1 and q equals to +1. Notice that in the case of quadrature phase shift keying, we have that all 4 coordinates also lie on a circle with a constant modulus. Now we have 4 points, therefore we have 4 possibilities. So for the 4 possible points, we associate each point with 2 bits. So if we have 2 bits, we have 2 to the power of 2 or 4 possibilities, which are shown over here. And we associate with each coordinate, with each symbol, the bits. For example, 0, 0 and 1, 0 for this coordinate and 1, 1 for this coordinate over here. So we have 4 possibilities that represent 2 bits of information. So 2 bits of information can be mapped to a symbol in the constellation. Each symbol will have an in-phase coordinate and a quadrature phase coordinate. Now, if the bit rate is designated as R sub b, then for every 2 bits, we generate 1 symbol. So the symbol rate will be the bit rate divided by 2. So this is a major point. By mapping the bits, in this case 2 bits, to points within the constellation, in our case shown here 4 points, we are able to achieve a symbol rate which is half the bit rate. Now let's go to the case where we actually have 16 constellation points. So this is called 16 QAM, or quadrature amplitude modulation. Since we have 16 points, each point can represent 4 bits. So we have 2 to the 4 or 16 possibilities. In this case, every 4 bits is mapped to a symbol. So the symbol rate is the bit rate divided by 4. Now since the symbols are then modulated and sent over the channel, then we can theoretically achieve high throughput, high bit rates by using more and more points in the constellation. And this is a key method in which we can achieve high throughput or high bit rates over band limited channels, is to map the bits into more and more points in the constellation. For example, in OFDM 802.11a, we use 64 point QAM in addition to 16 QAM. So if we have a fixed bandwidth, we can actually increase the throughput by mapping bits to points in a constellation and then modulating these symbols in the constellation. Now, as there's a limit to the throughput we can achieve through a channel, because every channel is either power limited, which means you have a restriction on the signal-to-noise ratio. You have nonlinearity in the channel due to the power amplifier in the transmitter and nonlinearities in the receiver. We have to deal with fading multipath channels, which create numerous problems. And one is of course intersymbol interference and the need for equalization, channel equalization. and also the fact that you have deep fades, and for particular carriers or frequencies you have very low SNR that degrade the performance. You have phase noise in the PLL and other non-idealities that limit the amount of points that you can have in a constellation, and therefore the throughput you can achieve over a band limited channel. Let's take an example of 256 QAM, where every point in the constellation would represent 8 bits. Now in some systems we can, by proper design, we can support 256 QAM, but 256 QAM requires higher signal to noise ratio. As the points get closer and closer together, then the noise causes errors in the decoding process. So there is a limit on the bit rate you can support over a band limited channel given a signal to noise ratio. Also, a 256 point QAM would require high linearity in the power amplifier and also in the receive gain, and it also has a problem of a high peak to average ratio. So if we intend to increase the throughput by using more points in the constellation, then we have to have more complex designs, and we should also meet signal to noise ratio requirements. If we take a look at the Shannon-Hartley capacity theorem shown over here by this expression, if W is expressed in Hertz, then C, the capacity of the channel, is expressed in bits per second, and we note that there is a limit on the signal to noise ratio. One way to increase capacity is to increase the signal to noise ratio, but if you have a bound signal to noise ratio, a fixed signal to noise ratio, and also a limited bandwidth, then your capacity has an upper limit. By the way, this capacity is the capacity of the channel in which you can, below this rate, you can achieve arbitrarily lower and lower error rates, close to zero. The Shannon-Hartley capacity theorem gives the capacity, the maximum achievable capacity over that channel. However, to achieve this capacity, you would have to use more and more complex transmitter and receiver architectures, and of course does not specify how to achieve that. Recently, using advanced coding techniques and more complex designs, we are getting close to the Shannon capacity limit. However, the expression is very useful, that it shows that we have a basic limitation based on signal to noise ratio in terms of the achievable capacity over a band limited channel. This expression also shows the trade-off between bandwidth and capacity. That is, we can trade signal to noise ratio for bandwidth, and this is used in spread spectrum, for example. We won't get into much of this detail, and we will defer that to later. Consider the quadrature phase shift king modulator that we show here, block diagram. We will discuss this in detail and go over all the blocks. This block diagram will go a long way into understanding QAM, or quadrature amplitude modulation, and how we can achieve high throughput over bandpass channels that are bandwidth limited. Consider the data source that generates ones and zeros, binary ones and zeros with equal probability. For example, we have a sequence shown over here, and we take every 2 bits and map them to a constellation point as shown. So we have 2 bits, so for every 2 bits we have 2 to the 2 or 4 possible constellation points that we show over here. Now as we map these 2 bits to a constellation point, every constellation point is a symbol that has an in-phase term and a quadrature phase term, as shown over here, I sub k and q sub k corresponding to the kth symbol. Now, if the bit rate is r sub b, the symbol rate is 1/2 the bit rate in this case, because we're mapping every 2 bits to one symbol. And this way we can achieve a higher throughput than binary phase shift king, or just, in which case we map a 1 to one symbol and a 0 to another symbol, typically in a BPSK system, or binary phase shift king system. So in a binary phase shift king, the symbol rate is equal to the bit rate, and our throughput is limited. But in the case of QPSK, since we are mapping 2 bits per symbol, then we can double the bit rate through the channel, since every symbol represents 2 bits. At the receiver, every symbol would be mapped back to 2 bits, but in the case of BPSK, every symbol will be mapped to a single bit. So the more and more points in the constellation, the higher our throughput. For example, if we had a 16 QIM system, then every point in the constellation represented by 4 bits, and the symbol rate would be the bit rate divided by 4, and our throughput would be 4 times the throughput of BPSK or binary phase shift keying. So going back to the data source, we have the data generating the ones and zeros. We have a block called the QPSK mapper, which takes every 2 bits and maps it into a point in the constellation. We have an in-phase term and a quadrature phase term, which together form a complex number you may think of as a complex number with a real part and an imaginary part, or in-phase term and quadrature phase term. In many cases, we will represent this symbol as a complex number. However, in actual processing, since we are splitting the symbol into its 2 components, then each chain represents the processing of a real number. Just as in the case of the binary baseband digital communication link we had before, we take the symbol, upsample it, and generate impulses, which each impulse represents the symbol, and that is input to a square root Nyquist pulse shaper, which has impulse responses, whose output is a superposition of the impulse responses corresponding to each symbol. And here we show the signal in the time domain, where we have a superposition of impulse responses of the symbols +1 and -1 that are the possible values for I sub k, and we have a superposition of them, and as before we can actually form the I diagram, and we have 0 intersymbol interference at this point because we are using Nyquist pulse shaping. Here we have the modulator. Our intention is to modulate this signal, this baseband signal, up to a carrier frequency of Fc. So we have the oscillator and we have the mixer, the multiplier. So at this point we have actually modulated the signal up to the carrier frequency F sub c. Now on the quadrature side, we actually modulate using the sine 2 pi Fc of t. So this phase shift of 90 degrees, we have sine of 2 pi Fc of t, so we modulate using the sine. Then we subtract it from the in-phase term, the modulated in-phase term, and we get a real signal over here, which is a double sideband suppressed carrier and centered around the carrier frequency Fc. The signal then goes through a multipath channel, and then we have additive noise, and we receive the signal at the receiver, in which we go through the demodulation process. Now we are going to analyze this signal here, and we will show how we demodulate it. The demodulator is shown over here. We basically take R sub t, the received signal, and using the oscillator running at 2 pi Fct, the same carrier frequency as a transmitter, we're assuming coherent demodulation. We multiply it times the incoming signal, and we'll show how that then translates the signal back to baseband plus a double frequency term, which is then filtered out by the Nyquist square root Nyquist pulse shaper. And at this point we get the signal, which we show the I diagram with a channel with additive noise only, no multipath, and we sample at the maximum I opening, and we receive the estimate IK of the transmitted symbol. Similarly for the quadrature phase term, however in this case we multiply times sine of 2 pi Fct. Again we get the baseband term and a double frequency term. The double frequency term is filtered out, the baseband term is also filtered, and we get the, because of the match filtering, we also get a I diagram, and we sample at the maximum I opening, which is at this point over here, and we obtain a estimate of the quadrature phase term. We also downsample back to the original symbol rate. If we take the symbols over here and create a scatter plot, we obtain the scatter plot shown over here, which is our original QPSK constellation. However, we have noise, and you can see the clouds around the actual ideal symbol, QPSK symbol. And this is the scatter diagram we can observe based on the demodulated signals. This block here is a QPSK demapper, which takes the in-phase and quadrature phase terms and using a minimum distance decoding algorithm maps each received symbol back to the bits, the original transmitted bits. However, we can have errors in the channel, and we will derive or show you the probability of error for a QPSK digital communication link. The QPSK demapper for maximum likelihood detection operates as follows. For any point that we receive in the constellation here, we find the distance of that point to the ideal constellation points. In this case we have 4, and we select the constellation point which is closest to this received symbol. Then we assume that that was the original symbol that was transmitted and map it to the bits, and that's the maximum likelihood decoding algorithm. So it's very simple. When we receive a symbol, find its distance to the constellation points and select the one with a minimum distance. That'll be the optimum maximum likelihood decoder, provided that the symbols were equally likely. So let's go over the quadrature demodulation process. So we have the received signal here, and we're ignoring noise. And as you recall from the transmitter, r sub t is equal to I sub k cosine 2 pi f c of t minus the quadrature term times sine of 2 pi f c of t. Of course, both of these terms are orthogonal, and as we will show in the demodulation process, we can actually extract I sub k independently and q sub k. In the quadrature demodulation process, we have an oscillator and 2 mixers, and the top rail for the in-phase term we multiply or mix with cosine 2 pi f c of t, and the bottom for the quadrature we mix with sine of 2 pi f c of t. Let's focus on the top part for now. So if we take the received signal r sub t shown over here, multiply times cosine of 2 pi f c t, we obtain the expression over here. So we get the cosine squared plus sine 2 pi f c t times cosine 2 pi f c t. If we look at this expression, we have the cosine squared of an angle, and we have the sine of the angle times cosine of the angle. So let's use these trigonomic identities. One is the identity shown over here, which is used quite often in communications. Cosine squared of alpha is expressed as 1/2 plus 1 plus cosine 2 alpha, or it is expressed as double the angle. Cosine alpha times sine beta, which we have a term over here, is equal to 1/2 of sine of alpha minus beta plus 1/2 sine of alpha plus beta. So if we use these trigonomic identities in the expression above, let's focus on the cosine squared alpha term. We obtain a term which is 1/2 times I sub k, which is shown over here, and we have a term which is twice the angle, which is this term over here, so we get cosine of 4 pi f c of t, and this is at twice the frequency of the carrier. So this term is a harmonic at twice the frequency of the carrier. For the case where we have sine of alpha times sine of beta over here, sine of alpha minus beta, we have 2 pi f c t minus 2 pi f c t, which is 0, so that becomes 0, and since the sine is 0, so that term drops out. And we get 1/2 times the sine of the sum of the angle. So we take 2 pi f c t plus 2 pi f c t, which gives us 4 pi f c t. So again, we get a term which is at twice the frequency of the carrier, or the second harmonic, and we've highlighted both of these terms over here. Now both of these terms will be filtered out by the square root Nyquist pulse shaper, since that's a low-pass filter. So these terms will be filtered out, and we're left with a baseband term, and we are left with a baseband term which is then filtered. Now, as we pointed out, we actually have I sub k times p sub t, which is the transmit pulse shaping filter, which we don't show over here but actually exists, and therefore we have a match filter here for that pulse shaped piece of t. We sample at the optimum timing. We are assuming perfect timing recovery. We sample at the time of the maximization of the SNR. We downsample back, we obtain the estimate I sub k, and a similar process we obtain the estimate q sub k. As we've shown over here, once we get these estimates, we have the constellation points, and then we can decode them back to the originally transmitted bits. We we have possibility of errors due to the noise in the channel. Here we want to discuss the issue of complex envelope and how we can use complex modulation and then get the actual real modulation, the quadrature modulation, by simple operation. First, consider the fact that we can represent each point in the constellation as a complex number x of k, and we will use this notation quite a bit in OFDM. So x of k equals I sub k plus jq sub k is a complex number. We have the complex exponential for the carrier, e to the j2 pi fc of t, which can be represented as a cosine term plus j, a sine term. Now, we form the signal r sub t, which is the complex symbol in the constellation x of k times e to the j2 pi fc of t, and we refer to r sub t as the complex envelope. Now let's substitute for x of k and also for e to the j2 pi fc t based on the two expressions here, and then group the real part and the imaginary part. And we notice that r sub t is just the real part of the complex envelope, capital R sub t. So if we take this part right here, then it's the same as r sub t over here. So we can actually represent r sub t, the quadrature modulated signal, as the real part of capital R sub t, which is a complex envelope. Now this is very important because now we can represent quadrature modulation based on the diagram shown over here. We take the symbols in the constellation, which are complex numbers, pass them through the transmit filter, for example a square root Nyquist filter, and then modulate it using the complex modulation e to the j2 pi f sub t, and we get the complex envelope. And to get r sub t, we just take the real part. Now here we can actually show the whole modulation and demodulation process using the complex envelope. So we take x of k, which are the complex symbols from the constellation, we apply pulse shaping, we do a complex modulation e to the j2 pi fc of t, we go through the complex channel, so we represent the channel as a complex channel, and then we do the demodulation by multiplying by e to the minus j2 pi fc of t, which clearly cancels out e to the j2 pi fc of t. We're left with x of k g of t. We pass that through the match filter shown over here, and since we're dealing with complex, we actually have the conjugate of g of t, and we have g of minus t because this is a match filter. And when we do the convolution and sample at the optimum sampling point, we get x of k back. So this is a nice compact representation of quadrature modulation and demodulation, and we will use it in OFDM. This also shows the process of taking a baseband signal, in this case symbols in the constellation, modulating up to a carrier frequency fc of t, passing it through the complex channel, and then demodulating them down and getting the signal back. And of course, for different carrier frequencies, we can occupy different channels, and we can actually build up a multi-carrier system, which is what we will discuss in OFDM. Now in 802.11a, we have multiple constellations that are used depending on the signal-to-noise ratio. For low signal-to-noise ratios, we use binary phase shift keying, which is shown over here, where we have only 2 points in the constellation, one at +1 and one at -1, similar to the baseband communication system we discussed earlier. We have QPSK, which we just discussed, and in which case we have 4 points, so we have 2 bits that are mapped to a point in the constellation. We also have 16 QAM, in which we have 16 possible symbols in the constellation, which can be represented by 4 bits, which are shown over here. So here we achieve a higher throughput than in the case of QPSK, but we require a higher signal-to-noise ratio since the points in the constellation are closer to each other. In this case, we have a 64 QAM system, and for the case of 64 QAM, we're actually mapping every 6 bits to a symbol. So every symbol represents 6 bits, and we have 2 to the 6 or 64 possibilities. This diagram shows the constellation for 64 QAM, It also shows the constellation for BPSK, but notice that the distance between the constellation points for BPSK are much larger than the points for 64 QAM. And this picture highlights the fact that if we're using the same power, then when you transmit BPSK with the same power as you're transmitting 64 QAM, then you achieve a more robust communication length, and your probability of error is much smaller because the constellation points are further apart. And as we showed earlier, the probability of error depends on the distance between the constellation points. The larger the distance, the lower the probability of error. This is a very important diagram which plots the probability of error, probability of the symbol error, versus the EB over N0 ratio. So the EB over N0, where EB is the energy per bit and N0 is a one-sided noise spectral density. And recall that we derived this expression, the probability of error versus EB N0, for the case of binary signaling, which is equivalent to BPSK. Now here we show the probability of error versus EB N0 for different modulation schemes. This curve here, we're showing the result for 4-level QAM, which is just QPSK. So 4-point QAM is the same as QPSK, quadrature phase shift keying. And in this case, we obtained the curve shown over here. And notice that again, at EB over N0 equals to 10.5 dB, we get an error rate of 10 to the minus 6. For 16-point QAM, we obtained a curve over here. Now notice that in the case here, we need a higher EB over N0 ratio or higher signal-to-noise ratio in order to get a probability of error of 10 to the minus 6, but we achieve a higher throughput compared to the case of QPSK shown over here. So if we have higher and higher signal-noise ratios, we can support at 10 to the minus 6 symbol error rate, higher and higher throughput. This curve here is for 64 QAM, and we see that EBN0 is around 20 dB. So when you have higher signal-to-noise ratio, we can support the higher throughput cases. So we can actually change rates depending on signal-to-noise ratio. And in advanced modulation schemes, this is called rate scaling. And by adding intelligence to the communication link, the actual link can adapt to the different signal-to-noise ratio scenarios in which the transmitter and receiver are closer or further away. Then we can adjust the rates accordingly. So again, note that when we have a low signal-to-noise ratio, we can only support, for example, QPSK, and we cannot support, for example, 16 QAM because we'd have a very large symbol error rate. Only when the signal-to-noise ratio is increased, then we can switch over to a higher throughput 16 QAM type modulation. So this illustrates also the necessity for rate scaling when we have cases of high SNR, and when the SNR is low, we have to downshift to, for example, QPSK or BPSK in order to achieve reliable communication over the link.